Okay, sorry about the delay. So the next speaker is Christopher Heidi, and he's going to be talking about the stable retraining of conversational agents. So you have the floor.
Good morning. I'm Chris Heidi. This was work done at Google with my colleagues Faye and Rahul. So being able to reproduce a trained machine learning model is important in both an academic and an industry setting. In an academic setting, it's necessary to be able to make meaningful comparisons between experiments. And in an industry setting, it's necessary to ensure consistency across user interactions. So users will expect features to continue to work that already exist. And if they suddenly break, that can lead to a great deal of frustration. And so what causes reproducibility issues? It may be due to updating the data or continuously retraining the model in a production environment. It may also be due to changes to hyperparameters or other hidden settings that are not publicized. But even controlling for all of these factors, there's still some non-determinism in the training process. And this is due to using different random seeds, or the order that the data is presented when using a stochastic gradient descent. And the reason that we see these reproducibility issues is because of underspecification, where there are many equivalent but distinct solutions to a problem. And this is especially a problem for deep neural networks, where there are many local minima that will produce the same top-line accuracy on a held-out test set, but will make different predictions for individual examples. And so for this work, we study the problem of prediction churn, where the goal is to make sure that models make the exact same predictions when they're trained on the exact same data and hyperparameters, but initialized from different random weights. And we study this in the context of conversational semantic parsing, where the goal is to convert a user query into an executable logical form. And the reason that we study this task is because it has realistic applications where it's often used as the backbone for virtual assistants. So for example, a user may be interacting with a virtual assistant and they have a query that is related to the weather. And so in one instance, the system may respond with a weather-related attribute. But the kind of scenario that we want to avoid is that when the user interacts with the system later, and the system instead produces an intent related to the road condition. So we build on previous work in studying prediction churn for classification tasks. And we extend this to structured prediction, which is a common frame for semantic parsing, where we are trying to predict a semantic parse as a sequence of tokens. And this is a more complex task for structured prediction because in many cases we are decoding a sequence, and mistakes made early in prediction are harder to recover from. And this is kind of borne out in our initial experiments. So even with the 12-layer base BERT model as an encoder, we find that across multiple training runs, the model predictions only agree around 80% of the time. And so even a 12-layer BERT model, it may not be feasible to serve this in an industry setting. So we also conduct experiments using a smaller model. So with a 4-layer BERT model, the agreement problem is much worse. So across training runs, the predictions only agree around 75% of the time. And so we apply a number of different methods that were used in related problems. Ensembling, for example, increases reproducibility, but is very expensive to use in practice because it requires training, storing, and serving multiple models. Distillation was introduced to address this problem, where it reduces the inference time, making it feasible to serve a model in that setting. And distillation has also been found to result in better modeling of uncertainty and resulting in better calibrated models. These experiments were done mostly on academic data sets, but we're also interested in exploring which methods work best when we introduce noise into the data. So this is the kind of scenario that we might see in an industry setting where instead of having only gold data, we might have some noisy labels introduced by some distant labeling process. So we make contributions in a few different areas. We introduce measures for identifying improvements in structured prediction churn. And then we also apply existing methods in a simulated realistic setting where we use smaller models or we distill from larger models and we explore ensembling and distillation. And then finally, we create data sets with simulated noise, where we will modify existing data sets with noisy labels. So in order to identify improvements in prediction churn, we first need to measure it. And because we're interested in how these models perform over multiple runs, we'll aggregate over n training runs, where a training run is the same model, but trained from a different random initialization multiple times. And so we use the standard exact match accuracy, where this is measured by whether the predictions match the target. And since we're taking n runs here, we take the mean of the exact match. And in this case, this requires the entire sequence to match. But EM doesn't tell us anything about the relation of the predictions to each other. So we also introduce an agreement metric, which requires that all n predictions across the training runs match each other. But the problem with agreement is that it doesn't take into account the relation to the target. And no practitioner would trade off agreement for accuracy. So we also introduce a measure for exact match at n, where the goal here is for all n predictions to match each other as well as the target. And so these measures are strict in the sense that they require the exact sequence matching, but our results will show that there is a significant difference across methods, even with these strict measures. And so we conduct experiments on 4 different data sets. So we use the top suite of data sets, top V1, top V2, and the English partition of MTOP. And then we also report results on SNPs. And our papers have a lot of results for each of these data sets as well as these metrics. But for this talk, I'll just report the average across the data sets and focus only on EM and EM at 10. So just to give an example of what these measures look like. So taking an example from the top data set, if the target is loop music, but across multiple runs, we have 2 different runs that make different predictions. So in this case, only the first run agrees with the target, whereas the second one doesn't. And so this would receive an exact match score of 0.5 since we're taking the mean, but both agreement and EM at 2 would be 0 since the predictions disagree. And so given these measures, we run a number of different experiments applying methods in a realistic setting. So for the baseline model, we use a pointer generator where we will encode a query as a sequence using a transformer. And this encoder is usually a pre-trained model such as BERT. And then for decoding, we auto-regressively generate a sequence of tokens in a semantic parse. And so at each time step, we will produce a probability distribution over the set of tokens. And during training, we'll use the standard cross entropy loss over the data. For our experiments, we also use label smoothing, which is commonly used in distillation. And the reason that we do this is twofold. This has been known in previous work to reduce overfitting when using distillation. And we also want to see how these different methods perform in a noisy environment. And label smoothing can be thought of as a form of noise injection, where we are introducing a uniform prior across the vocabulary. And so averaging across the results across the 4 data sets, we report the mean across 10 runs as well as EM at 10. And relative to a larger model, the smaller 4-layer BERT model obtains close performance to a 12-layer BERT model. There's a loss of a few percentage points in accuracy. But the biggest gap is when we measure EM at 10. So ideally, this EM at 10 would be much closer to the EM performance. But when we measure this across multiple runs, we find that there's a 10 percentage point gap. And really, we want that gap to be much smaller, if not identical. So we explore a number of different approaches to try to reduce this gap, using different flavors of ensembling and distillation. So in the standard ensembling case, this requires training K models. And this is also what we do for our task, where we train these models using cross-entropy loss on the data. The main disadvantage of ensembling is that it requires K times the resources of training a single model. And it's possible to do all of this in parallel, so the actual runtime might be different, but it still requires K times the resource usage in terms of compute and storage costs. During inference, we also require K models. So we take the K models, and at each time step, we take the mean of their respective probability distributions. And then this gives us a single distribution at each time step, where we can then proceed as usual using greedy or beam search for decoding. But inference here, again, requires a K-fold increase in cost for both for compute and for storage. So this means that ensembling may not be feasible in many practical cases. So we can think of ensembling as kind of an aspirational upper bound, where our goal is to approach the ensemble using less resource-intensive methods. And we do find that the ensemble qualitatively improves on both EM and EM at 10, where there's a small gain in EM, but more importantly for our task, it reduces the gap between EM at 10 by quite a bit. So we can see that ensembling helps with reproducibility by reducing the prediction churn. But because ensembling is expensive, we are also interested in exploring applications that don't use as many resources. So in the standard distillation setup, there's a 2-stage process that requires first training a teacher and then a student. And the teacher may be an ensemble, or it may be a larger model that we want to distill from. So in the first stage, we train a teacher using the standard cross-entropy loss on the data. And then we train a student using cross-entropy loss as well, but combining it with distillation loss from the teacher predictions. And so distillation, here it will take at least 2x the training cost, depending on the size of the teacher model. So since the teacher model may be much larger, this may be an even larger increase. Unlike the ensemble, the disadvantage here is that this can't be parallelized because it requires training the teacher model first. But the main advantage of distillation over ensembling is that there is no latency increase during inference. We can just take the student model and we can serve it as is. However, on this task, we find that for different flavors of distillation, we find that there's no significant improvement on our measures. So exploring both a 12-layer BERT encoder as a teacher, as well as using a throughway ensemble of smaller models, we find that there's a very marginal difference in both EM and EM at 10. So this also motivates exploring other types of distillation. So we study and we conduct experiments using co-distillation. And the main difference here is that instead of training a teacher as a first stage in this process, we apply the standard co-distillation setup, which means training multiple peers in parallel from scratch. And so instead of having a student teacher, these peers will distill into each other while also being updated using the cross entropy loss from the data. And here there's still a 2x training cost if we have two peer models, but it's also parallelizable. So it has the advantages of the ensemble in that case over the standard distillation setup. And then unlike the ensemble, here we have the advantages of distillation where we can just take one of the peer models and use that for inference. And then we find that co-distillation qualitatively improves over the baseline, where we most significantly don't do worse in terms of EM, but we are able to close the gap a little bit between the baseline and the teacher, obtaining half of the performance improvement of the ensemble on exact match at 10. And so these these initial experiments were conducted on the academic data sets, but we are also interested in simulating a kind of noisy environment that we might see in a practical setting, where we don't always have gold labels and we might have some distant labels as well. So we introduce noise to the data sets in two ways. First, by randomly swapping some of the tokens, and then also by introducing systematic noise. And so for our first experiment, we take the existing training data and we randomly swap some percentage of the intents and slots with other intents and slots respectively. So for these experiments, we find that the baseline performs much worse in this scenario, as we might expect, but the ensemble is able to recover some of that performance gap. And then here we find that co-distillation performs the best in this scenario, but it does even better in the noisy setting, where we're able to obtain close to the ensemble performance for both EM and EM at 10. For the second type of noise, we introduce systematic noise, whereas random noise may not be the most realistic setting, since it's not necessarily the case that the data would be corrupted in that sense. But we try to simulate a process where data is generated using another model. And one way to do this would be by taking a model and using it to label the training data by taking the first position on the beam. But this, in many cases, the first position on the beam will exactly match the gold label. So instead, we take the second position on the beam, which gives us data that will both be systematic and will be incorrect. And so we train a model on some held out partition of the data, and we label the remaining held out partition. And so for 10% systematic noise, we again find that co-distillation performs the best in this setting. So overall, we find that co-distillation consistently offers the best performance in noisy environments with a small increase in costs relative to other methods.
So we have like 3 minutes for questions. So are there any questions? Okay. Okay. Thanks for the talk. You have been kind of leveraging models as a whole. I was wondering if there is the potential of working on ensembling models that are sharing layers, and that would simplify maybe the training and inference.
Yeah, I think so. That yeah, in our experiments we didn't explore that too much. But I think like even in the co-distillation case, it's still expensive since during training, since we need to train entire models separately. But I agree that there's potential there, since the encoder is already using like a pre-trained model. So there might be some gains by just using the decoder, for example, and sharing the encoder.
There was another question.
Oh, yes, for the talk. I have a question about the co-distillation. So what exactly is used as the cost function for the distillation loss? And if there is some sophisticated strategy for the update, or you just update in every step, both the models, or?
Yeah. So we are using cross entropy for the distillation loss, and for the losses, the two loss terms, we just combine them linearly. So we are updating at each time step. But I think there is potential in future work for something more sophisticated instead of just kind of doing this linear combination.
Yeah, thank you.
So last question. Yeah, or yeah.
Thank you. So how did you, for the ensemble case and the co-distillation case, how did you initialize your, I mean, how did you get the different models? Did you take specific care to diversify them?
Yeah, so for the different models, we just did random initialization. But I think there would probably be avenues for future work in terms of doing smarter initialization, but that wasn't something we focused
Thank you.
on.
Yeah, I guess we should move on to the next talk. So you guys can probably take it offline.
Again.
So we have the next speaker.